In this screencast, I'm going to look at evaluating the Taylor series of a function of two variables, a function f of x and y, and I'm going to evaluate it about the point xy equals ab, and I'm going to assume that this function is sufficiently differentiable for me to be able to do this. And what I've done at the very top here, in this result that I'm putting a box round, is I've written out what I consider to be the most concise form of the Taylor series representation. What we do in practice is just look at the first few terms of this sum, and that's usually good enough for our purposes. And what I've done here is I've written out, in fact, the first four terms in the summation, and I will then illustrate this with an example afterwards. I'll just talk you through these terms. If little n equals 0 in that boxed result, what I end up with is just the function evaluated at the point about which we're finding the Taylor series. If I let little n equal 1, I end up with the linear terms that should hopefully be familiar to you. And let me just talk you through what this means. That bit there, partial df by dx brackets ab, that means find the derivative first, so differentiate f with respect to x, and then, once you've differentiated, evaluate it at the point x equals a, y equals b. Similarly for partial df by dy evaluated at the point ab. The next terms, which are these ones here, are the quadratic terms obtained by putting little n equal to 2 in the formula above. And the important thing to notice here is that I have a 2 there, and that's coming from the mixed derivative, that basically what I've got here is a partial d2f by dx dy, and I should also have a partial d2f by dy dx. And because those two are the same by the mixed derivative theorem for the functions that we're interested in, I end up with that doubling, and I end up with the 2 there. And that's in fact the 2 that would be obtained if I let little n equal 2 in that formula there. I'm squaring out that bracket, which is a differential operator bracket, and I end up with the 2 coming out when I square that bracket out. If I then look at the final line that I've written out, that's with little n equals 3. And I hope you can see that I'm now getting the Pascal's triangle coefficients coming out for when I cube a bracket out. I've got a 1 there, just multiplying the first bracket, then I've got a 3, then I've got a 3, then I've got a 1. And what you could perhaps do now, if you're not quite happy with this, is stop this recording for a moment and see if you can follow that how these terms that I've written out follow from the boxed result at the top. See if you can satisfy yourself that that does hold. Once you've done that, I'm going to illustrate it with an example. So let me now look at an example, and I'm going to look at a function of xy which is sine of x times y, and I'm going to evaluate it about the point x equals 1, y equals pi by 2. And in fact, I'm going to only go up to the quadratic terms because that should be enough to show you what's happening. So I'm only going to have to evaluate up to and including the second derivatives. Before I do that, when I come to evaluate, to write out the Taylor series, I will need to evaluate it, this function at the point 1 pi by 2. So if I do that now, you can see that the function is 1, and that's going to be my first term in the Taylor series representation. What I'm now going to do is find the other derivatives, and I'm going to use some shorthand notation here. F subscript x just means partial df by dx. And if I differentiate sine of xy with respect to x, I get cos of xy multiplied by the derivative of xy with respect to x, which is just y. And similarly, if I differentiate sine of xy with respect to y, I get cos of xy multiplied by x. Now let's look at the second derivatives. I'll do the straightforward ones first. The second derivative with respect to x, I've just got to differentiate this term again with respect to x. And if I do that, hopefully you can see cos differentiates to minus sine of xy, and I get another y coming out, so I end up with a y squared. And similarly, the second derivative with respect to y will be a minus x squared sine of xy. Again, if I'm going too fast for you here, do stop this recording, pause it for a moment, and see if you can work out what these derivatives are and check that you agree with me. Finally, I'm going to work out the mixed derivative, partial d2f by dx dy, and there's two ways of doing this. I either differentiate partial df by dx with respect to y, or I differentiate partial df by dy with respect to x. And ideally what you should do is both of those and check that you get the same answer in each case. If you do, the chances are you're okay, and if you don't, then certainly something's gone wrong somewhere. I'm going to take the first of these and I'm going to differentiate it with respect to y, and so I have a product here. So I differentiate the first term, the y. Let me just ring this so you can see what I'm doing. I'm differentiating this expression with respect to y. So I differentiate the y and I get a 1 multiplying by cos of xy, plus, and I write down the y and I differentiate cos of xy with respect to y, which gives me minus sine of xy. And that's what I get if I differentiate partial df by dy with respect to x. You can check that you do get the same thing. So what I'm now going to do is evaluate all of these terms at the point x equals 1, y equals pi by 2. And I'll do this in a different colour just so that you can check what's happening. Fx at 1 pi by 2, well, that's actually going to come out to be 0. I've got pi by 2 cos of pi by 2, so that comes out to be 0. And similarly, partial df by dy comes out to be 0. That's not usually the case, it's certainly not necessarily the case, but in this case I will not have linear terms when I write out my Taylor series. The second derivative with respect to x, when I evaluate it, is going to be minus y squared times by sine of pi by 2, which is just 1. So I get minus pi squared over 4. And similarly for this one, when I evaluate it, I'm just going to get a minus 1. And finally for the mixed derivative, which I'll squeeze in here, I'm going to get minus pi by 2. Again, I may have gone too fast for you. You can check those later if you want to and check that you get the same answers out. And it's these numbers here that are the coefficients of the x minus a, y minus b brackets in the Taylor series representation. So what I'm now going to do is scroll down and start to write out the Taylor series representation of my function. And what I've got is, I'll write this out longhand first, it's going to be f evaluated at 1 pi by 2 plus x minus 1 df by dx evaluated at 1 pi by 2 plus y minus pi by 2 partial df by dy evaluated at 1 pi by 2. And then we get the quadratic terms. So I get 1 over 2 factorial x minus 1 squared, the second derivative with respect to x, plus twice x minus 1 y minus pi by 2, the mixed derivative, and then finally the second y derivative. And if I needed to, I would now go on and do the next term, the n equals 3, the cubic term, in the summation. And that would give me a more accurate Taylor series. But for our purposes, this is sufficient. What I've now got to do is put in all of these values. And they've disappeared off the top of the screen, but I've written them down. The ones that perhaps you do remember are that is 0, and also that is 0. But I also had that the function at 1 pi by 2 was just 1. And the second derivatives, the second derivative with respect to x, that was minus pi squared over 4. The mixed derivative was minus pi by 2. and the second derivative with respect to y was -1. So I had those written down before. You can scroll up the top of the screencast to check those if you want to. And what that means is that I can now write out my Taylor series. The first term is 1. Then those linear terms disappear because they're both being multiplied by 0. And then I've got 1 over 2 factorial, and I've got x minus 1 squared times by minus pi squared over 4. I've then got plus 2 lots of x minus 1 y minus pi by 2 times by minus pi by 2. And then finally I've got, in fact that's going to be a minus sign, isn't it? I've got a minus y minus pi by 2 all squared. So if I just tidy that up in the final line, I've got 1 minus pi squared over 8 times by x minus 1 all squared. Then I've got minus, and the half and the 2 will cancel, so I'm left with pi by 2 x minus 1 y minus pi by 2. And then finally minus a half y minus pi by 2 all squared. And in fact, because there's an infinite number of these terms, I should just put a plus dot dot dot. If I choose to truncate the series, I will get the Taylor polynomial, but that's not what I've chosen to do in this case. So the series in fact goes on. So that is the final answer. I'll just put a box round it. This is the Taylor series approximation to the original function, up to and including the quadratic terms. And we would leave this like this. We wouldn't multiply out the brackets and simplify, because if we did, we'd lose the important information that when x is close to 1 and y is close to pi by 2, these brackets, x minus 1 and y minus pi by 2, are very small. And when they're raised to a power, they get even smaller, and that's important. That gives us more of a feel for how this solution is behaving, so we will leave it like this.